In preparation for CVPR, we want to talk about some of the main topics that we're looking at. And that doesn't mean that those are the most important topics or that we have any academic viewpoint on what really matters right now in computer vision or none of that. It's just what we as a fund think is important. What we're looking for is what we call the humanoid robot pipeline. So that's one, and then the other is the um, the the self-driving car pipeline. So those are the two things that we're focused on. Just as a caveat, we believe that eventually those two fields will merge, and that whether a robot has legs or wheels is not going to matter that much. We believe in the Platonic representation of intelligence, but that's for another episode. I think what we want to focus here is just give people a preview of what we care about when it comes to CVPR. We're not going to be physically present there, but we're going to be virtually present. So we're going to follow some presentations. So what is the humanoid robot pipeline? The humanoid robot pipeline is learn from video, so pre-train at scale, internet scale, learn from video, then mid-train, teach skills, and then fine-tune. So the same idea that has worked with language can also work with robots as far as the architecture is concerned, or as far as the actual process is concerned. Now, of course, the details are very different. Okay, learning, let's say, pre-training in robot world is very different than pre-training in language world. But I just want to put this out to understand what we're looking for, and then the self-driving car situation there, I think we're going to focus actually on simulation, because the safety concerns with self-driving cars, in our opinion, are solved. Tesla has a general self-driving car that can drive in almost anywhere, but the tail end needs to be solved with simulation. In other words, you have to put as much situations you can, as much action jumps you can in distribution. So the car, which is really memorizing action jumps, can act in the most unusual circumstances. And maybe as a sort of side note also, we want to talk a little bit about reasoning, which is sort of the Alpha Mayo approach, which we believe can help also in solving the tail end. This is an Underground podcast. It's May 30th, 2026. This is Crimdelco. For the year, we're up 90 basis points. The market's up 10.7. We're underperforming by 9.8%. So CVPR is coming up. It's the computer vision and pattern recognition conference that is, I think, rapidly turning into probably almost as important of an AI conference as Europe's is. It doesn't cover all the aspects of AI, but because computer vision is so central to physical AI, and general intelligence, in our opinion, is driven by physical AI, we can almost argue that CVPR is the AGI conference, because that's what AGI is going to sort of emerge out of, if at all. Now, what we're looking for, and for new listeners, maybe just a little background here. Why are we even talking about conferences here? We're a hedge fund. We make money investing in companies. And the reason we do that is we're in the knowledge business, so we try to really cover the broadest spectrum of knowledge accumulation, creation, maybe distillation possible. So we go to academic conferences, we talk to companies, we read books, we read novels, we attend academic seminars, we occasionally even take a class here and there. So we really try to understand where is the crossroads, or where do academic developments, technology, and entrepreneurship overlap. That's fundamentally what we're trying to do. Sometimes we're right, sometimes we're wrong. We've been wrong this last 6 months because we haven't invested properly into the value chain for agentic workflows, and that has been the story of the last 6 months. But we believe that we still have enough legs to go with our portfolio and the real world AI that we're actually investing in, which is really our big thesis that we think will generate the kind of value creation that we're expecting to make. So CVPR is the most interesting conference from our perspective because, again, real-world AI is driven by perception. Computer vision is the workhorse of perception, and therefore you have this what should I say? It's almost not. It's really nice overlap between what the academics are doing and what we think can be taken away for our investment thesis. So, what is the humanoid robot pipeline? The humanoid robot pipeline is pre-training, mid-training, fine-tuning. Pre-training is, and we're using the same analogy like in the language world, it is raw, internet scale data trained on a transformer model that is able to understand relationships between tokens and therefore compress knowledge in latent space. The knowledge that we're looking for is action, state, action, states and transformations. So we're looking for states. So the robot is in the kitchen with its arms spread. That's the state. And then the action chunk is one arm goes and grabs a bottle and puts it in the fridge. That's the transformation. And then there's a new state. So we're looking for a plethora of these types of images or videos, to be more precise, because we're looking at 4D here. We're not just looking at images, but we're looking at the time dimension in there or dynamics in there too. We're going to talk about physics in a second, but what we want to capture is dimensions of okay, what's the state and how does it transform? So this has been done already with the self-driving car technology that Tesla has developed with FSD. So this has been done. This is, I guess, FSD is a proof of concept that this works. It requires lots of data, lots of time, but it works. Now, how do you train at internet scale action chunks and so forth? Well, you need to find a way to transform video into virtual space and then train in virtual space and then do the sim to real and close the morphology gap to the real robot. Simply because you can't have robots go around the world, destroying things until they figure out how to do things, particularly if it's reinforcement learning based. So if you want to not give the robot too many priors, in fact, almost no priors, and there's a really interesting lecture that I just attended by Carlo Sferrazza. I think I might be butchering his name, but he's now assistant professor at UT Austin, postdoc with Peter Beal, and PhD from Zurich, ETH Zurich. So he's working on very interesting problems for pre-training, which is, for example, a way to translate video movement, human video movement into robot movement, and then also interesting approaches towards exploiting symmetries, like, for example, when you move your arm relative to your torso, there's a certain symmetry of your arm. There aren't that many action spaces available to the arm. For example, it can't be behind you, it can't be 10 meters away from you, things like that, right? There's a certain locality that can be exploited, and he's using actually transformers, so attention technology to exploit that. And then also there's the symmetry with the surroundings. Again, if you're walking up the stairs, you are not going to be 10 meters above the stairs. You're not going to be flying or something like. There's certain things that we can sort of reduce the action space based on where you are. So, like he says in the presentation, these are priors. They still allow for end-to-end learning. So the priors are not constraining some sort of end-to-end. This is not a human-induced heuristic. This is just simply if you're walking upstairs, you're walking upstairs. You're not somewhere else, and your action space is defined by the stairs and your own torso. Like there's a lot of things you can still do, but you can't ice skate while you're going up those stairs. So whatever. I mean, I guess you get my point. So that's what Carlo is trying to do. And I think this is it's one of those presentations that really nicely match with our thesis and with what we think Tesla is doing with Optimus. We're not so sure whether Tesla is exactly doing that, but Musk has spoken about it. We're going to train the humanoid robot exactly the way we train FSD. So we're going to use a massive amount of video data and then go from there. So that's the one thing we're going to focus on at CVPR. And then the next step is the mid-training. And that is, so once the robot has this knowledge, this latent space defined knowledge of the world, the states, and the actions that transform states, then we're going to teach the robot skills. That's where physics comes into play. That's where screwing a screw, fixing a door, fixing a car, fixing a GPU in space, the things like that that we think we can use robots for will certainly be developed in the mid-training phase. I don't have too much knowledge right now how this is done. I think the robot factories are one way to approach this. So when you have but what you want to have is you want to have this pre-trained knowledge, because that allows for generality, that allows for chain of thought, that allows for reasoning. So you can't reason if you don't have a body of knowledge to reason from. And I think that's why pre-training is so important. But we're going to focus on the mid-training, and then the fine-tuning is really sort of the make the robot, let's say, human-friendly, make it act in a certain way. That the fine-tuning is, I guess, the where you starting to induce behavioral heuristics. They're still learned and they're still adaptive, but they're a bit more like, okay, I want this robot to be always kind and gentle with the elderly person when it takes care of the elderly person, like that kind of thing. That's the fine-tuning thing. So this is going to be the focus that we have as far as humanoid robots are concerned. As far as self-driving cars are concerned, we're going to focus on simulation, because I think the pre-training and mid-training and fine-tuning of self-driving cars, as we speak now, driving in a Tesla on actually 12.6, not even 14.3 FSD, proofs in the pudding. I think the problem of self-driving has been solved, general self-driving. Now it's the tail end, the regulatory issues, business strategy, things like that are still holding large-scale deployment back. But we're definitely, I mean, we just, we're using it every day, and therefore, I think when the product works, then you don't need to argue anymore about whether it works or not. So, but the interesting part of self-driving is really the tail end, and that can be solved with simulation. So the question then is, what kind of simulation do you use? And I think self-driving lends itself really nicely for simulation, because you don't need to understand physics too much. I mean, there's a little bit you need to understand. You need to distinguish between IC roads and not IC roads and things like that. But overall, I think you certainly don't need to have as much dynamic knowledge as you have with rural robot. So, but you need to simulate all these weird things that can happen, the construction side, the man waving you to come, the man waving you not to come, things like that. There's a lot of things that still are out of distribution, or that could be a problem, a convenience problem, as Musk calls it, because you could have a situation where, let's say, you block traffic and those sort of things. So we're going to focus on that. I think Jitendra Malik is one of the professors that works on this, that we follow. There's others, and yeah, we're Bay Area centered here. We're based in the Bay Area, so we spend a lot of time at Stanford and Berkeley. That doesn't mean other people's work is less important or anything. We just, again, you have to start narrowing down your scope a little bit particularly when you go to a conference like that, because there's 10,000 people, thousands and thousands of presentations and posters. You just can't grasp all of this unless you have a very focused mind, and that's hopefully what we're working towards. So to summarize, CVPR is coming up. We're going to focus on the humanoid robot pipeline, the pre-training for video, the mid-training skill acquisition, and then the final fine-tuning. We're going to look at how video training works in particular, so how the morphology gap can be closed between humans that we can follow through videos and then learn from them. and teach our human robots a basic fundamental sort of action, state action uh, uh, know-how. And by the way, this is one of the theses that we developed recently, which I think is very important, which is the reason we have humanoid robots, and that is actually a promising technology, is because we can learn from humans. So that's important. We have one example of a four-limbed, intelligent thing going around, the human doing things, and we can replace a lot of those things with robots by just learning from the humans how they do things. So that's a very important insight. And then the other thing we're going to focus on is self-driving cars, and over there we're going to focus particularly on simulation technology. I think simulation is still underrated in the space of AI, particularly real-world AI is all about simulation. I mean, if you think about it, every difficult engineering project, SpaceX launches or battery technology for electric cars or whatnot, like every time you push the boundaries of new technology in real space, you have to rely on simulation because you can't just build. Even SpaceX doesn't have the capital to constantly blow up spaceships. So you need to simulate as much as you can to reduce your action space, or I'm paraphrasing Jennifer Doudna here, we want to use AI or simulation I mean, at some point it's going to become the same thing. We want to use AI to reduce the amount of experiments we do. In other words, we let the AI do all the experiments, we let the AI do all the try and error, and eliminate all the sort of low probability success experiments, and then really focus on the ones that we think have good success and implement those in the real world. And the same applies to every other engineering project. Anything we do in the real world is always constrained about time and cost and risk and safety. And if we can reduce the amount of tries that we do in the real world and focus on the high success rate, and that we can do by simulation, then I think we have a much better chance to move forward and actually be much faster in terms of developing new technologies. Thank you.